Okay, so let's talk about strain. So we've been dealing with rigid bodies, pushing on stuff, so on and so forth. Bodies aren't actually rigid. When you push on something, it moves, it flexes, it deforms, it changes its shape when forces are applied to it. So this deformation occurs when stress is induced in the object and or when there's a temperature change. So we'll talk about, we'll be dealing with the stress-induced one in this lecture. So obviously we need to be able to measure this, we want to quantify it. So we have the concept of strain. So essentially, when you have some sort of force applied to the object, you can take measurements of a line on an object and before and after loading, and essentially strain is what we use to define how those lines change shape. So like change their length basically, or how various lines on the object change their orientation relative to one another. So the angles in between them. So a normal strain is what changes the length of an element. So essentially something that makes something smaller or larger, or what have you. So they change the length in one direction over its original length. So again, sign convention, we're working the same. Normal strain has the same sign convention as normal stress. When you pull on something, it gets longer. So when you have a normal strain, it's positive when the length increases. So the positive strain is a tensile strain. We get this increase in length. So delta L, or just small delta, is sometimes used to denote that, and then that'll be that divided by the original length is what we use to determine our average strain in that specimen. Shear strain, basically. So if we start with a rectangle, if we start with a square, if we're looking at a square element and we push on it on the top and hold it on the bottom, then it's going to deform, and it's going to deform in a manner that looks like this, and it's going to change the angles. So this was originally a right angle, and now its new angle is going to be pi over 2 minus this here. So again, we're worried about the change in the angle, so our shear strain is going to be that value there. And that'll be measured in radians. We basically always use radians when we're dealing with shear strain. And yeah, so it distorts so that lines that were once perpendicular are now at a different angle. So there's a small gamma is used to denote that. So for sign conventions, we're basically matching the sign convention for shear stress. So if we've got a coordinate system like this here, x, y, and z, if we apply a positive shear stress, so this here would be an XY shear, and here again a YX shear on this face, because like we saw in the last video, where those things kind of have to match one another. So essentially, if we apply a positive shear on the X face, if we apply a shear acting in the Y direction on the front X face, that's going to be a positive shear, and that's going to cause it to deform like this. So essentially, if you're looking at something in the XY plane, then that'll cause the leftmost corner, sorry, the bottom leftmost corner and the top right corner to get smaller. And that'll mean that this angle here goes from, well, 0 to something. And kind of the same thing works when you're looking at something in the YZ plane or the XZ plane as well. So this will be a positive shear, and essentially, if we had something where it was never mind. if it was fluxing the opposite way, so essentially causing it to move in this direction, then that would be a negative shear. So yeah, as we can see here, stress, like strain, we can define it as a tensor. So essentially, we can have our strain defined in terms of the kind of the values we talked about, and the directions they're acting in. The strain in the x direction is just going to be the change in the x value of the distance per unit x. Same deal here for y, same deal here for z. For the shear strains, unfortunately, we actually, these values here are going to be essentially half of what we talked about here. So when we're talking about this, we were defining what we call the engineering strain. The strain tensor, unfortunately, it works a bit differently. The problem is that when they went and defined the concept of a tensor in mathematics, that happened about 100 years after engineers had started measuring strain. So in mathematics, basically, the concept of a tensor kind of needs to work the same way. So essentially, the EY here, the EXY needs to be kind of be based upon the average of this distance here divided by this distance here, and this distance here divided by this distance here. Which, if we average those out, those work out to be half of the engineering strain, because you'll see that if we'd taken this parallelogram here and had it oriented like this, you'll note that this angle here. Basically, if we take this parallelogram here and kind of lay it flat, this angle plus this angle is going to be equal to that angle there. So it'd be double what we kind of saw. So yeah, a bit of a mismatch between the concepts that we were seeing in that kind of mathematics came up with and what we'd been measuring it as. That having been said, most of the time when you're working with shear strain, you'll be working with engineering strain. So you'll typically be focused upon this, and you won't be as worried about this. So yeah, just the tensorial shear strain is defined by that, and our engineering shear strain again, is just defined by this here. So it works out to be, similar. Just we'll have to multiply one of them by 2, or divide by 2 to get to the other one. So we'll do a quick example here. We've got this plate. It's being deformed into this shape shown, and we need to basically figure out what the average normal strain is along this side and the average shear strain in the plate at A relative to the X and Y axes. So we'll just get that real quick. So one thing I would like to note is that anytime we're dealing with this, we're assuming that the distortion that actually occurs is relatively small. So we're able to make the small angle approximation. So essentially, when we get this angle here shifting over to here, the angle is small enough that basically when we go to kind of calculate the the new y distance here, because we can basically make the small angle assumption that cos theta is going to be equal to 1. So any change in the y here is basically assumed to be entirely due to the normal strain rather than due to the shear strain. So if it's moving down relative to that point, that's because we're pushing down upon it. It's not because we're pushing this way and that it's shifting a bit. So that's basically going to always be the case. So we've got that. So if we want to define our, come on. So we've got our strain in the X. That's going to be equal to 0. We know that because basically this segment here, AC, that doesn't change at all. Got our strain in the Y. And again, we tend to follow the same convention that we saw with the stress, is that if, an epsilon xy is obviously the shear strain in the xy plane. An epsilon xx is the normal strain in the x-plane. If they just say epsilon x, then that implies normal strain in the x. If they only have the one, then that's implying that you can just add a second one on there and it means the same thing. So we can, same thing. Same thing. So in this case, that would just be, so because we're making that small angle approximation, all of this 2 millimeter drop here, that's only due to the normal stress that is applied. So that'll be based upon this. So it is going to be -2 millimeters divided by 250 millimeters. That's supposed to be millimeter, not a meter. So -0.008. What's the units on that? Well, it's a ratio, right? So it's unitless per se, but millimeter per millimeter if you want to put a unit on that. One thing that's nice about the fact that it is a dimensionless ratio, or it's a ratio that's where the dimensions cancel out, is that when you're working, is that a strain will be the same regardless of what unit system you're working with. So a 0.008 strain will be exactly the same if you're working in imperial or if you're working in metric. So again, this, I'd like to emphasize that this is a negative 2 millimeters because it's getting smaller. So if we want to go back to kind of the original the delta L, so our delta L, that's going to be 248 minus 250. So our new minus our old gives us a negative 2 millimeters. So getting smaller will cause you to have a negative strain. That is compression. And then we got our shear strain here. So what we have here is we need to figure out what kind of how this angle changes. So again, because this here didn't change at all, we know that that this 3 millimeter shift here, that's entirely due to the shear that's imposed. It's not being caused by the it's not being caused by an normal stress. So the entirety of that 3 millimeter shift is due to the shear strain that occurs. So we just need to basically figure out kind of what this angle here is. So we're left with just keep in mind that we are going to be working based upon the 3 millimeters. That is going to be a positive shear strain because the angle in the bottom left corner gets smaller, or the angle in the top right corner gets smaller. So we started out here, and we are moving over. We started out with this, and now we're left with this, so that gets smaller. Or alternatively, this type of distortion can only happen with a positive X force applied on the top, or applied on the front face of the Y, on the front Y face. So it's a positive shear stress being induced, which means that this is a positive shear. So anyways, it's a positive shear. It's should be relatively easy to calculate here. So we are going to go ahead and make the small angle approximation, which is basically saying that when we're working with radians, that tan of our angle is going to be equal to the angle. So essentially, our angle there is going to be, in radians, is going to be 3 millimeters over the 248 millimeters. 48. So that equals 0.0120967. I'm going to throw all those in there because if you want to figure, we'll just kind of test the validity of the small angle approximation here. So the inverse tan of that is going to be .0120996. We finally got to a 2 instead of a 7. So the small angle approximation is perfectly valid out to, what do we got here? 1, 2, 3, 4, 5, 6 digits. So, that is accurate enough for the vast majority of your applications. Typically speaking, I would expect And if you're actually using this, that's probably about as accurate as you ever need to be. So anyways, that is how we go about to solving our shear strain and our normal strain for those two situations.